Hello and welcome to another video on orbital mechanics. I'm still going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition. I haven't done a video in quite a while because I've been quite busy, but I've got up to chapter 3 and this is a video on the elliptical orbits in terms of time. So let's get started. So to get the time of orbit so far, you need to use a few tricks with trigonometry, and the trick that they use generally is that they draw a full circle around the elliptical orbit, and they define a concept termed the mean anomaly, which is the angle that is covered in the same time period as the elliptical orbit. So here we have the elliptical time and from theta, and here is the time from a circular orbit with angle mean anomaly. So the mean anomaly is a simple definition for the period around a circle, which is 2 pi divided by the period times your time. And we know that the period of a elliptical orbit from previous chapters is 2 pi over mu squared upon h over square root of 1 minus e squared, all cubed. And then if we rearrange that, we can get the mean anomaly equals mu squared over h cubed upon 1 minus e squared to the power of 3 over 2 times t. So that's that. We'll at least save that for a moment. And then we will look at getting another value for t so we can relate it back to the angle theta. So up here we have the tangential velocity equal to the radius times the angular velocity, which we've seen before, and then the constant of h equals r times the tangential velocity. Combining those together, we get h equals r squared times angular velocity, and then replacing r with this here, and then integrating down here, rearrange a bit to this format. Then we integrate the left hand side and the right hand side. Left hand side is a constant, so it just becomes t, and the right hand side becomes this hideous equation that isn't detailed in the book. The book forwards us on to another book to look at that integration. I haven't worked it out, but if you want me to, leave a comment and I'll give it a go. We can then notice that this bit of the equation here and this are very similar to up here. If we just rearrange a little bit, we can get the mean anomaly equals 2 tan inverse upon square root, well, all this stuff, right? And then we just save that for now, right? We don't need to worry again until later. And then we are going to try and work out essentially the angle E here, I guess, right? And so this is the eccentric anomaly, and that is drawn on to give us a way to relate M and E, right? So by putting this here, we can get some angles and we can make some equations. So the one that we are going to make is this bottom distance here, and that is A cos E, which you can see via trigonometry. You've got A, E, and it's the cos equals adjacent over hypotenuse, so A cos E. This distance from O to F is AE, which we already know, and F to S is R cos theta, so that's R and then cos theta. So we can say that A cos E equals AE plus R cos theta. And then if we cancel our A's and replace R with our elliptical orbit formula here, we get this once simplified, and then we can rearrange that to be cos theta equals E minus cos E over E cos E. I'm saying E a lot, but there's a lot of E's in this. Minus 1, you can read it for yourself. And then using the sine cos identity here, we can get sine big E equals, yep, square root 1 minus eccentricity squared sine theta over 1 plus cos theta. And then you'll notice that this is, sorry, best an E out there. Yeah, this is up here, right? And then, so that's number 1. We can replace that whole section with sine E, big E. And then we can get another one for big E using some tan identities. So tan squared angle over 2 equals sine squared angle over 2 over cos squared angle over 2. And then the other half angle formulas for the top and bottom of that can be reduced down to 1 minus cos E over 2, and cos angle over 2, and 1 plus cos angle over 2. And then if we actually take our equation here and 1 plus it and 1 minus it on both sides, so like it's like 1 minus cos E, 1 plus cos E equals 1 minus E cos theta over E cos theta minus 1, and then 1 plus E cos theta over E cos theta minus 1. It's just adding 1 on both sides and then reducing it down. So it reduces down to these two formulas. Sorry about the mess. I accidentally wrote E earlier when it should have been theta. You can cancel the bottom on both. You end up with 1 minus cos theta upon 1 minus E over 1 plus cos theta upon 1 plus E. And then this 1 minus cos theta and 1 plus cos theta can actually just be replaced by tan squared theta over 2. So that becomes tan squared theta over 2, and then 1 minus E over 1 plus E. So you've got tan squared E over 2 equals tan squared theta over 2 upon 1 minus E 1 plus E. And then we just rearrange to get E. So that's that. Cool. And going back here, so that's our E, and that's exactly the same as up here. We can just replace that. So we have mean anomaly equals eccentric anomaly minus eccentricity sine eccentric anomaly. And that is that. I think that might be the quickest and simplest explanation of this I have ever seen, because it took me a while to reduce it down into its simplest and quickest explanation. If you think I've made a mistake, or you didn't understand or anything, leave a comment. And thank you very much. Goodbye.